Hi everyone, welcome to 5.5 Day 2. Today we're going to be talking about something new that we call differentials. And so before I talk about what those look like, I want to talk about what they are. And so first I'm going to just backtrack a little bit and remind ourselves, I'm just going to make some notes up here, talk about linearizations really quickly and kind of draw a comparison between linearization and differentials. So remember, the purpose of doing a linearization was to be able to approximate the value of a function. Right? So here we are approximating the value of a function using the tangent line. Okay, so the idea here was that we know that if we zoom in really close to a function, that function is going to resemble a line. So we said if we take the function or the tangent line to a function at a point, we can estimate the value of the function near that point of tangency using that tangent line. So that was a way of approximating a value. So differentials are also going to allow us to approximate a value. However, in this case, I'm going to change this wording here. Let's see. I'm going to take this off. So now with differentials, differentials really describe the approximate change in the value of a function in relation to a change in the value of x. So it describes the approximate change . Okay, the change in the value of a function in relation to a change in the value of x. So if x changes by so much, how much do we expect the value of that function is going to change? That's what a differential is. So here's what it looks like. We know that one way of denoting our derivatives is by y prime. Okay, the idea here is we can also use this other notation that we've used time to time, though probably less frequently. So dy dx, the derivative of y with respect to x, is equal to y prime. Those mean the same things. The nice and easy thing about differentials is that they're really just the derivative, but rearranged. Our formula is really simple. So now I want, my differential is just expressed as dy. So I need to get dy by itself. So essentially what we're just doing then to do that is I multiply both sides by dx. And now I have my formula dy is equal to y prime dx. That's my formula for a differential. And again, what that's doing is giving me the approximate change in the value of a function if x changes by a given amount. So that's what we're going to be working with today. So down here, hold on one second. Okay, so down here we're going to do a few examples. So our directions first say to find the differential dy, again, and that's related to this formula here. And then we're going to evaluate dy given the values of x and dx. Okay, so here's what this is going to look like. We know we said that this differential is just the derivative rearranged. So that's where I'm going to start with. I'm going to find my derivative, which is just dy dx. And then I know using my power rule, I have 5x to the fourth plus 37. So that's my derivative. And to get my differential, I just rewrite it. So I have 5x to the fourth plus 37 times dx. That's my differential. So that's the first piece of this. That's all they're looking for when they're asking for the differential. So now it wants me to evaluate dy for the given values of x and dx, and you can see where we have to plug those in. So now the value I'm going to plug in, I have x equal to 1, and my dx is 0.01. So now to calculate this, and here this is going to give me 5 plus 37 is 42, times 0.01 is going to give me a differential of 0.42. Okay, now what that's really telling me is that if x changes by 0.01, so if I start at 1 and I have a change in x of 0.01, then I have an approximate change in the function of 0.42. So that change in x of 0.01 leads to a change in the function of 0.42. That's all that this is telling me. So the next one, just for extra practice here, again, finding the differential. So the first thing is just to find the derivative. So my derivative, I have some chain rule here. So my derivative is going to be 3 times the cosine of 3x. Now, my differential, I just rewrite. So I multiply both sides by dx, so that I get 3 times the cosine of 3x times dx. There's my differential. Now, I'm going to evaluate that where x equals pi and dx is negative 0.02. So dy is 3 times cosine of 3 pi times negative 0.02. So cosine of 3 pi is going to give me a negative 1. So I have a negative 3 times negative 0.02. So it's going to give me a positive 0.06. Okay. So that's how we find differentials and then evaluate them given certain values. Now, for the next two, it's just asking me to find the differential. So in this case, I'm not going to be evaluating anything. I'm really just doing the first piece of this. Right, so this is asking me to find the differential if my function is tangent of 2x. So now again, we said our first part is to take the derivative. I know tangent of 2x, I have some chain rule there, so my derivative is going to be 2 times secant squared of 2x. And then find the differential. I know I have to have my dx at the end, and that's it. That would be my differential. Now, for my next one to find the derivative, here I'm going to have to use my quotient rule. So I'm going to have low d high minus high. Derivative of low is just 1 all over x plus 1 quantity squared. And so now we're going to multiply by dx. And I'm just going to see if we can do any simplification here. So I know on top I really have x plus 1 minus x over x plus 1 quantity squared times dx. On my top, my x's are going to cancel out. So really I have 1 times dx, or just dx in my numerator, and x plus 1 squared in my denominator. So that's how we find the differential. So now, when we talk about differentials, a lot of times we're going to talk about, coming up here on the next page, is differentiating or distinguishing between dy, which is our differential, and delta y, which is the actual change in y. So I'm going to make those notes here. Remember that dy is the approximate change in y. And again, just like, let me scoot that down, just like when we were doing linearizations, it's the approximate change in y, and we're using the tangent line to do that approximation. Okay, on the other hand, when we talk about delta y, this is our actual change in y. So what is actually happening to y when x changes by a given amount? Okay, so let's talk a little more about dy and kind of see what this looks like graphically. So the value dy, our differential, remember that dy is just our differential. It describes the change of the value along the tangent line when x changes by the amount delta x, right? The change in x or dx. Those are the same thing. So here's what we have. If I look here, so here's my original x. And so I can look over here, that's my point of tangency. And so I know I have f of x. Now, when x changes by the amount delta x, right, the difference here is delta x, my new x value is x plus delta x. And so when I'm looking at this, I know for dy, I'm estimating that change using the tangent line. So now I'm going up to my tangent line here, right? If I look and the difference in those values along the tangent line, that's what is represented by dy. It's the change in the function along that tangent line. Okay, and that's when we're calculating it, that's what we're doing with our differential, f prime of x dx. But just graphically, it's important to recognize that when we're talking about dy, it's the change along that tangent line. Now, the difference here with delta y, the value delta y describes the change in the value along the function, along that function itself when x changes by the amount delta x. So now when we're talking about this, again, here we have x, which is changed by the amount delta x, but now we're looking at the change along the function. So I have this point, I have my f of x, and now here, because I'm looking at the change along the function, I just go back up to the curve. One sec. Okay, sorry about that. Just had a visitor at the door. Okay, so again, when we're looking at delta y, we're looking at the change along the curve itself. Okay, so now I'm comparing f of x to this new value, f of x plus delta x. And that's delta y. So you can see that's a different change than what we were estimating with dy. So to calculate this delta y, it's just f of x plus delta x, right? My original plus the change that occurred, minus f of x. And really, this is just kind of what we think of as the top of our slope. It's just the change in y. That's all delta y is. It's the actual change in y. So let's look at some problems with this. Okay, so it says let y equals square root of x. It says find dy and delta y at x equals 4 with dx equal to delta x equal to 3. So we know for dy, right, that's our differential. And so we know we have to find the derivative. So dy dx is going to be 1 over 2 root x. So dy, our differential, is just dx over 2 root x. So now we're going to evaluate that. So dy is dx, which is 3, over 2 times the square root, x is 4. So if we simplify that, our dy is 3/4. So again, we're estimating that if x changes by 3, that the value of our function is going to change by about 3/4 if we're centered around x equals 4. Now let's look at delta y. Remember, delta y, we just said is the change in y. So I said f of x plus delta x minus f of x. Well, here, x was 4, our delta x was 3, so what we're really looking at is f of 4 plus 3 minus f of 4. So I have f of 7 minus f of 4. So root 7 minus root 4 equals root 7 minus 2. And so obviously we don't know exactly what that is, so just to get our value here so we can compare it to our approximation, I have root 7 minus 2, and I get 2.236. That's not correct. That is obviously not the right notation. Here we want root 7. I need to get out of that square root, minus 2. That looks better. About 0.646. Okay, so we can see this is 0.75. We're a little bit off, but it fairly represents that change. Now, here's one thing I want to mention that will come up when we start to look at AP questions. If I consider this curve, so we were looking at square root of x, okay, so it looks like this. So we're looking at x equals 4, right? And we're looking at that tangent line to estimate it. So I'm going to sketch in a tangent line here. So maybe I'll use a different color. So let's say this is my tangent line. We said the change when we look along that tangent line was 0.75. And that the actual change along the curve, right, was 0.646. So obviously here our change was an overestimate. That has everything to do with the shape of this curve. Because this curve is concave down, that's going to mean that our tangent line is going to be an overestimate. And you can see in this picture how that's going to overestimate that curve. So I just want to kind of make that note there. If our curve is concave down, then we know we're going to have an overestimate in our change. And again, we'll talk about that more later on, but I just wanted to make mention of that there. All right, in the interest of time, we're going to skip the next example and look kind of some more word problems. And we'll actually just do one more example, and then we can cover the others in class, and that'll give us a chance to address any questions that might come up. So let's take a look at number 3 here. So this question says the radius of a circle increases from A equals 10 meters to 10.1 meters. So use dA, which is going to be our differential here. Okay, we're going to use dA to estimate the increase in the circle's area A. So we want to know how much does a change in the radius impact the change in area. And so then we're going to compare this with delta A and then find the approximation error, which is just the difference between the two. So the first thing I need to do if I'm dealing with the area is I need to have an equation for that area. And luckily, since this is a circle, we know that is A equals pi r squared. So now if I'm going to find the differential, I need to differentiate A with respect to r. So I know that dA dr is just 2 pi r. So now my differential dA is just 2 pi r dr. So now I have my differential, and I'm going to go ahead and evaluate it. And I see here that I need two values. I need my radius, right? So here's where they're giving me that. Okay, now, so I'm going to plug that in, 2 pi times 10. Now, my dr, that's my change in radius. So my dr, which is the same as my delta r, right, must be the change. So since it went from 10 to 10.1, if I subtract those, I get the change. So that's just 0.1. So now, let's see, 2 pi r dr. Okay, now I know if I multiply those out, I'm just going to get 2 pi, and my units are meters squared. So I'm estimating that if my radius changes by 0.1 meters, my area is going to change by 2 pi meters squared. Okay, now it said to compare that to delta A. So delta A, remember, is just we're using our area formula, and it's going to be our new area minus our original area. So pi, the new area was 10.1, so pi times 10.1 squared, minus pi times my original radius, 10, squared. So for a minute here, I'm just going to ignore those pi's. So we're going to have 10.1 squared minus 10 squared, and I get 2.01 pi meters squared. So the actual change is 2.01 pi. My estimated change is 2 pi meters squared. So now if I want to find the error, I'm just going to subtract the actual, which is 2.01 pi, minus the estimated, which is 2 pi, and I get 0.01 pi meters squared. So that's the error in using that tangent line to approximate that value. So now, since we're already over, we'll leave the rest for now. We'll go over a couple more examples in class, and then as usual, you'll have time to practice with this.